We started out with a warm-up, finding the integral of x dx from 3 to 4. We found that if we graphed it, we had f of x, this is 3, this is 4. We could use the trapezoidal rule, or the area of a trapezoid, and we found that the area was 7/2. And that works real well for that kind of a problem where we have a definite geometric shape that we can find the area of. But it's not always so easy if we had, say, an integral from 1 to 2 of x squared minus 3 dx. And in a case like that, the graph of the function would look like this, but we have a curve and we don't have any geometric formula that would help us get the area under that curve. And so in that case, we use what we call the fundamental theorem of calculus. And that says that if f is continuous, in other words, if our function is continuous on the closed interval AB, and capital F is an antiderivative of f, then the integral from a to b of f of x dx is equal to big F of b minus big F of a. In other words, we evaluate the integral, we plug in b, we plug in a, and we subtract the value we get with a from the value we get with b. So if we go back and we look at that same problem that we started with, using this idea of the fundamental theorem of calculus, if we take the antiderivative of this function, we get 1/2 x squared. And if I evaluate that at 4 and at 3, I'm going to get 16/2 minus 9/2, which is the same 7/2 that we got before. Now, the fundamental theorem of calculus is one of those theorems that we use over and over and over again. I can't stress enough that it's f of b minus f of a, not the other way around. So let's look at that function from 1 to 2, the integral from 1 to 2 of x squared minus 3 dx. And we will integrate and plug in our limits. So when we take the antiderivative of x squared, we get 1/3 x cubed minus the antiderivative of 3 is 3x, and we're going to evaluate that at 2 and at 1. So f of 2 is 8/3 minus 6 minus 1/3 minus 3. And when we evaluate that, we get 8/3 minus 1/3, which is 7/3, and negative 6 plus 3, which is minus 3. Well, 7/3 minus 9/3 is a negative 2/3, and that is the value of this particular integral. When we graphed it, we did see that x squared minus 3 was below the x-axis from 1 to 2, and so we would expect to get a negative area. And sometimes it's a real good idea to think about, okay, what does that function look like? Is the area positive, or is it going to be a negative area? All right, let's look at another problem. If we go from 1 to 4 of 3 square roots of x dx. First step, I need to rewrite this as 3x to the 1/2 dx. So when we integrate, we get 3 times x to the 3/2 times 2/3, or 2x to the 3/2, and I'm going to evaluate that at 4 and at 1. Now the square root of 4 is 2, and 2 cubed is 8, and 8 times 2 is 16, minus 2, so here we get 14. Everybody loves the trig function, so let's look at a trig function from 0 to pi over 4. The integral of the secant squared x dx. Hopefully you remember that that is the tangent of x, and we're going to evaluate that at pi over 4 and at 0. So the tangent of pi over 4 minus the tangent at 0 is 1 minus 0, which is equal to 1. Now many times we'll have an absolute value problem. If we're taking the integral from 0 to 3 of 2x, the absolute value of 2x minus 3 dx. In a problem like this, we have to remember that this is not linear. There's a v somewhere, and we want to find out what is the x-intercept. In other words, what value of x will cause this expression to be equal to 0. So if we solve for x, we get x is 3/2. And if we think about what the graph looks like then, 1, 2, 3, at 3/2 is where the v occurs. And notice, here we have a positive slope. If we were to extend this down here, let me change the color. If we were to extend this down this way, we would have 2x minus 3. But the absolute value reflects this part and moves it above the x-axis. And so we're going to have to look at the integral. We're going to have to look at 2 separate intervals. Notice this has a slope that matches 2x minus 3. This is the opposite of 2x minus 3. So we're going to take the integral from 0 to 3/2. And we take the opposite of 2x minus 3. And we add to that the integral from 3/2 to 3 of 2x minus 3. You've been dealing with a property that says as long as this number and this number match, then it's the same as from 0 to 3. So if we take the antiderivative here, we get a negative x squared plus 3x to evaluate at 3/2 and at 0. And we get x squared minus 3x to evaluate at 3 and at 3/2. So when we plug in 3/2, we get negative 9/4 plus 9/2 minus 0 plus 9 minus 9 minus 9/4 minus 9/2. Well, negative 9/4 plus 18/4 gives me 9/4. Here this becomes a 0. And 9/4 minus 18/4 gives me a negative 9/4, but it's minus, so minus a negative becomes plus 9/4. So we get 18/4, which is equal to 9/2. The thing we have to remember about absolute value is that you have to break it up into 2 separate parts. Notice the positive slope and the negative slope. So we had to make sure that those match our numbers along the bottom, our boundaries. And one final problem that we want to work, we want to find the area that's bounded by y equals 3x squared plus 1, x equals 0, x equals 2, and y equals 0. So if we graph that, 3x squared plus 1 is going to look something like this. Here's x equals 0. Here's x equals 2. Now the y equals 0 just tells us that that is our bottom boundary. So we're looking at this area. So don't let the y equals 0 throw you. That's just telling you what the bottom boundary is, or what the area between the curve and the x-axis. So here we would just take the integral from 0 to 2 of 3x squared plus 1 dx. Integrate, we get x cubed plus x, and we're going to evaluate that at 2 and at 0. So we get 8 plus 2 minus 0, which is 10. So really a pretty easy lesson. Your assignment is page 284, 3 to 42 every third. I took up your homework, and you have a quiz that you need to make up.